professional activity or the consultancy. Because whatever we know it, so if that can be extended, say for solving the problems, so then it will be good. So that's a practicing it. Whatever you are teaching, so you try to practice it and give the solutions to the industry. And obviously the industry is going to so the benefit, otherwise they will be going out to get that specialty. Yeah, we since we have say some amount of the professional competency, say that we start actually doing the projects, say as and when come. I just only the listed, say the type of things, say that normally we do it. Valuation of projects, arbitration. This is for the younger faculty, say the how they can develop nicely to become not only as a good teacher, but as well you can become, say the good geotechnical or a rock mechanics specialist, where your importance is actually going to be immense because you are going to find the solutions. So from that angle, I'm listing it here, the different variety of things, so the which normally we do it. Geohydrological modeling, solution cavities filling, liquefaction studies, so well foundations, seismic site response, rock mass classifications, foundation treatment, geological and geophysical studies, analysis and design of different variety of structures, underground structures, so ground improvement, foundation design, landslides and stability of slopes, site characterization, tunnels and tunneling, testing, and design, providing the design parameters. Since we have a very good, so the laboratory, laboratories, so we do a lot of, so the testing as well. So we provide the design parameters and for the different solving the different, so the problems. Of course, so this is roughly giving, so the how our time is actually the spend on different, it's. I take, so the maybe 4 projects, so the here stability of Chenab bridge abutments, Subansari powerhouse slope stability, integrated effect of seismic and rainfall landslides in Himalayas, evaluation of bore tunneling practice in Delhi, and coupled hydromechanical modeling of slopes in upper catchment of Bias in the Himalayas. I will see it, so there, but I will be definitely closing it, say by 1 o'clock. So that ends my presentation in this segment. And if required, I will take in the second segment, or maybe we can close it, so there with this. So these are the case studies. So case studies are always, so the very interesting. And as you know, like, so the Chenab is our mighty river, and across that, so the bridge is supposed to be constructed by the railways. So the valley is getting, connected with the train from Jammu to Baramulla. So in between, so you have, of course, so the Benihal to Baramulla, already, so the trains are running it. But Jammu to Benihal, so in between, so you have this a river called, so the Bias, the Chenab. Across that, so you need to have a bridge. So this is, so the lowly end, and then this is, Katra end. So from Jammu is this side, and when you come, say through a tunnel, and you will be entering into the bridge. What is the? There are hundreds of bridges and hundreds of tunnels are being constructed, so they here. This is a mighty river, Chenab, and a tributary to the Chenab is, Anjikad. Anjikad Valley is also this. It is a tributary to the Chenab. Here also, so you need to have a bridge. Originally, both are actually the planned as, arch bridges. In the arch bridges, so you don't have any piers. You don't have any supporting, so the piers, and there is a viaduct part, and then there is a arch. Arch is, so the obviously arch foundations are coming here, which I call is, so the P50, and then this is, P40. So say both the bridges, so the originally the planned, but this bridge is now, say cable stayed bridge. They made it. I'm not going to talk about the Anji card, but I'm going to talk, say very briefly about the Chenab, so that. So that's what actually the Katra, Jammu Katra, and then say the that is the Chenab, the crossing. So this particular bridge is coming, so the here. And then I also said that so the Benihal, this is that off route, so they is still yet to be opened. Hopefully, say if these two bridges are done, and this will be continuous journey from Jammu to Baramulla, and cutting across, so
Please do not talk unless
एक होटल वो हॉस्पिटल वाला किया की डेली वाले जो करा रहे हैं 8 वीक.
Sorry, sir.
no issue. Shall I continue, sir?
Yes, you can now continue.
Yeah. So Jammu to Baramulla, very nice, cutting across the scenic beauty of Kashmir, so they will be able to enjoy it once these two bridges are done. So one bridge is, so the this is the Chenab, and Anji Ghat is also, so the this particular bridge. I'm not going to talk about this, but this is the bridge which I am talking about it. So the specialty is this. You see this, Eiffel Tower. Eiffel Tower is, say 324 meters, and Eiffel Tower se bhi, so the ye uncha hai. And from there to there, so it is almost like 1.5 kilometers. And abutment to abutment arch abutment. If you see it, say that this is this is from there to there, so it is almost more than a half a kilometer. That is 505 meters, so there is what actually the width, so they here. So the total height, so the up to the water level, it is 359 meters. It's a mind-boggling, so the height, even the Eiffel Tower. Some of you, so the definitely might have seen the Eiffel Tower, so the in Paris, and that is only 324 meters, and the deck to the water level is going to be 359 meters. So imagine that, so you are traveling on the valley, and looking down, so the 359 meters, it is a thrilling experience. So this is going to be the highest the arch bridges in the world, and the second highest is going to be the Anjikat bridge. So both these bridges are very unique. Now, of course, so the early diagram, so they're all hypothetical, so it is all architectural, because the bridge is not yet done completely, and I will show you the present scenario. But when we enter, so this is the scenario. So it is a viaduct part, right side, the river is going down, and the arch is going to come, so from there to there, something like that, so that. So there is a drifts which are actually created, and we captured, so the what is the bottom formations, how they look like. This is the downstream side, and against to the downstream side, the foliations of this rock is, so there. The rock which is present is, so the dolomite. Dolomite is magnesium calcium carbonate. So it's a very good rock, but having, so the lot of, so the foliations. As I said that the foliation plane is one joint, and then J2 and J3. This is one set of joint. This is another set of joint. This is so each one will be playing a different role. It is very rough, so thereby the friction will be very high here, and whereas, so the J1 is, so very smooth. So the issue here is there was a controversy when the bridge is actually, the constructions are actually going on in full swing in 2008, and suddenly it was altered because somebody said that, say the bridge is unsafe. The global stability of the slopes are not done through the discontinuum mechanics. The persons who are knowing numerical methods, so you do have two branches of numerical methods. One is continuum mechanics, and the other one is discontinuum mechanics. Here in the continuum, most of the time, so we do the continuum mechanics based models, so like FEM, FDM, and BEM. And in that, so you must be familiar with the flag, phase, or flaxis, abacus. These are all different numerical codes which are available to solve the stability problems and other geotechnical issues. We are assuming that so the joints here is so continuous through and through, but here you are treating that joint is not continuous and there are bridges and gaps. So this is a discontinuum mechanics related thing, and DM and discontinuous deformation analysis. This is more complex because one single joint from through and through, you are assuming it here, but here so it is not that the same joint is actually the cut into pieces. And how do you do the modeling? So to do the modeling, so the numerical codes are there. That is the UDEC and so the 3DEC. I'm talking about the scenario in 2008 when this was needed, and we did this particular analysis using the UDEC and 3DEC. The mandate is, so to prove the using this particular code, establish the global stability. So thereby, uninterruptedly, the bridge construction will be going on, will go. So I'm just only putting very few slides. So this is a big lecture. I'm not actually doing that because only just to give how we can say solve the important national problems, national issues, so that so we will have so the better solutions. So it is a earthquake prone area. So obviously it should be done say in the dynamic conditions. So this is what I'm saying. The joints are not continuous. There are breaks are there, and the joint spacing is an issue. So you need to simulate what is exactly available in the in the site, and try to simulate say those conditions and do the modeling. And normally when you do the slope models, so it will be 30 by say the 20 is meter square, or say the 30 by 30, 30 by 40. That is the type of slopes normally we do the analysis. But here the slope, look at six more than say the 650. That is the width of it, and the height is almost 450. So 500 by say 600 area you are trying to model, every location so the one can have it, since it is a bridge. And we make a cut slope where the piers are coming, where the abutment pier is actually the coming, and we put say the monitoring points. These monitoring points will actually give you the full stress and the deformation history because of the different loading conditions, not only on the surface, but at 10 meters below, thinking that so when we do the foundation excavations, definitely into the rock, so the 10 meters or so these foundations goes. So thereby at that location, so what is the condition. So, of course, so to get some experience, we did the limit equilibrium using the continuous, continuum mechanics based modeling, and then subsequently, so the UDEC and 3DEC modeling we did it. But in this, so the main crux is, so the getting the right parameters for the analysis. The project authorities, so they give some properties, but we didn't, so the convince with those properties. So thereby, we put a additional 6 months, so to do the intensive characterization of the material under the different loading conditions, which I projected earlier. So that experience, that research, that experience of doing different things, so is what is what helps us so in deciding so the correct the parameters. So okay, what is this? Yeah.
This is slide.
Okay. So these are the material parameters are important, and why this is slide is not moving. Yeah. So to cut the story short, so we did that, so the different modeling, and the factor of safety is, so the comes, so the 1.96 and around, and the most critical thing is, so these cases, these cases, you have taken the complete joint conditions which are prevailing there, and also the peer loads you are taking it, and then seismic loads. So thereby this case becomes, so the very critical, and even the critical case under the dynamic condition, it is coming 1 point, so the 6.3, so it is fairly safe. Of course, the analysis is, so the very comprehensive, that requires a separate, so the special lecture. Now you see that, so because of the analysis which has been done, the project is, so they put it online, and then the bridge is actually vigorously getting, so constructed, so then now this is that viaduct part which is, so the being constructed. So these are the piers, and the abutment piers are almost like, so the 130 meters, so the height. It is a tremendous, the slope cutting is, so the is so intense, say this is the abutment pier coming here, and then so the next other, so the P 30 for 20, and so the 10 piers are coming in one side, and then there are other. So P40 looks like this, so the dimensions of this particular excavation is 50 by 36, that is the base width of, so the foundations. And now you imagine that the machinery to move and the hill, how much cutting is actually done here is a mega project. So bridge is this is coming up, so they very nicely, and our services, so they have helped this project, so the put on the rails. Otherwise, this has gone into the major controversies. Now, I give you the brief about, this particular Subansiri hydropower project, which is, so the in Subansiri River is a tributary to the Tista, and it is between, so the Arunachal and then, so the Assam, and it is again, so the mighty river. And Subansiri hydro project, once it is commissioned, this is going to be the highest hydroelectric project done by the Indian government, because the capacity is, say 2000 megawatt. Everything is set. Only thing is, say some small local issues, so they are holding this, but I think very soon these things will actually get cleared. The general plan, if you see it, for any typical hydel project, for the youngsters, to understand, the river is actually the flowing it. You are trying to construct, so the dam. When you construct the dam, so the obviously you will be doing the excavation. So you need to divert it the water. So thereby you have, so the diversion tunnels are there. You are taking the complete, so the water and putting the downstream into the river, but this is getting dried. So to take, so the further precaution, you create, say the coffer dam. It is a temporary dam, and another, so the downstream side, another coffer dam. These two coffer dams, say completely seals the water not to enter into the chamber into this particular location, so that the dam can be constructed. And once the dam is actually constructed, and this will be so the closed, and then these two coffer dams will go, and then there is a intake, so the tunnels are there. This intake, the reservoir water, so they will be taken, and then, so it will be used for running the turbines. So thereby this is a surface powerhouse. Our problem is, so is related to this. Uh, the mountains are there, that hills are there. This is such a very compact, so the project, very close knitted, so the project, and your HRT tunnels are not very far, so the they are very close, and the powerhouse is, by the time, from the powerhouse water comes, so that it is already reaching the the river level. So for getting the space, so to construct the powerhouse, they cut the hill. Okay, cut the hill. It is properly engineered slopes, and original profile is that. But then, so they cut that, and then they put the shotcrete, the rock bolting, etc. It is properly designed slope. So thereby you will be able to construct, so the construct the powerhouse there. What happened? This is there are 250 into 8 HRT tunnels. So 8 tunnels are there. So they're already done. The slope is made. The slope is 160 meters height slope, fully engineered slope. But then, this is what actually happened, so the when the construction for the powerhouse is actually the picking up, so then this slope, so the came crashing, because there are some issues are there. You have, so the major fractured zones are there. Somehow, so they were not able to recognize when the investigations are done. And after doing everything, so then the slope, so the started collapsing it, except only the first tunnel, but the rest of the seven HRT tunnels, so the completely closed. What are the causes for the failure? Is a simple textbook. These are the things which we study it, so in our textbooks. The shallow shear zone. So your shear zone is running. First of all, you should identify that there is existence of shear zone, and it is almost, so the very less overburden. Unfavorable joint systems, they are all dipping. They are dipping towards the valley. Any slope, so the having the joints or the formations dipping towards the slope, so then it is a dangerous. Heavy rainfall, excess water. What is that rainfall is going to do it? Earlier we discussed that, so it creates the pore pressure. And what is the type of rock? It is a shivalic sandstones. From the west to the east, so you have the shivalic sandstones are there. They are very soft. Their strength is not, so the more than 20 MPa or so. And under the water, the strength decreases, so the drastically. So when you are making such a huge amount of cutting, the stress is actually the getting released. Stress relaxation is also going to create, so the cracks into the system. Rock wedges are actually the falling. It intersection of two sets of joints, so they give you the rock wedges. They are also, so the seen. Steep slopes, so the making it, so the 50, 60, 70 degrees slopes, so the will not do in this type of. And also it is a earthquake prone area. Dynamic loads are there. Repeated seismic loads are going to create, so the destabilize the slopes. And ineffective drainage system. See, when you create a slope, so the obviously we create, so a lot of weep holes. Weep holes are actually to drain the slope, so the totally, so that in the dry condition, so the slope is going to have higher strength. But if the water is whatever the water which is actually there, this is actually remaining, so the there that produces, additional pressure. So all these classical, so the reasons are the real cause for the failure. And then you always, as a consultant, you come in the last minute, you won't be having the sufficient time for investigating the material and the methods, etc. You as a expert, so that you need to give a quick fix solution. The solution should actually work. If it is not working, so then the whole blame is actually going to be put on the. So it's a critical. So thereby, as an expert, so you have to be very careful, when you are accepting the projects, because unless you are competent, so you should not actually take, because the whole blame is going to come onto you in case if it is not working. So what are the support systems we have? We have the shotcrete. Shotcrete is a pneumatically exerted cement slurry onto the rock face. So once it gets cured, so it forms a very nice, so the cover up, and create a good stable slopes. And also in addition, you get so the rock bolts, because the immediate layers which are actually the fractured, then they can be stitched with the rock bolts. Rock bolts, by tightening it, will create a compressive zone, and because of the compressive zone, so the slopes or the underground structures will become stable. Wire mesh. Wire mesh is so the is associated with the shotcrete. We put with or without wire mesh, so we do the shotcrete. So these two or three methods are good enough to do any type of so the underground construction or the slope stabilities can be created so the for most of the projects. Now what we did is so we did a lot of mapping, and these are the joints which are actually dipping towards the that at different sections. This particular area looks that this is the collapsed area, out of the slope. uh, this area is almost 70% of the slope is so the collapsed, and we rebuilt it by dividing into different segments and did the analysis, and all these things are actually the showing that so the before and after, what is the improvement, so the factor of safeties that has been, and then how we rebuilt it, rebuilt it. So um, this is the rebuilt, and now the powerhouse is actually the done. The project is so the waiting for the a lot of probabilistic analysis etc has gone, because it is analysis should be created so the in the dynamic conditions, so since it is in a highly earthquake prone area. Another important thing, we always say that so the landslides occurs because of the water permeating into the slopes. So water is a culprit, definitely. And most of the landslides happens so the in the month of July, August, September, or so in the Himalayas. And apart from that, so the landslide, the earthquakes are also going to create, problems. We have earlier seen that cyclic shear testing results into the easy sliding. So the same thing happens, so the if the area is also earthquake prone and the rainfall is also intense, so then it becomes a deadly. It becomes so the deadly. Major failures are taking place due to the rainfall, and also during that time, if happens to be an earthquake, so then contribution from the earthquake is also going to be there. One such classical thing is there, so that is a Paglajura and Teen Daria. So in the Darjeeling Himalayas, okay. So two major landslides we take for the study is a massive landslide that is actually occurring, and then there is a toy train. So the classic the Darjeeling, so the heritage train which is actually there, that is come the road, the track and the road is completely collapsed. So they here you can see it from the top. So aerial picture, if you see it, so its impact is so much. There is a railway yard is there, so the constructed in 1850s or so. So that is also getting, so the getting affected because a lot of collapse. How do you do it? Different material, it is not a bouldery, it is not soil, it is not rock. You do have, some mixed type of failure modes, and it is a massive, and we took the complete basin and the water potential also, so we monitor the piezometers to get the pore pressure at the site along the slope. And also, like the first time we did the analysis, say through this particular device. This device is again, so the designed by our students, and you can measure the impact of the rainfall. That's when the rainfall is actually happening. It not only the intensity, but also the impact of the rainfall is going to be there on the slope. So intensity, duration of the rainfall, and also, like so the earthquake, because during this time only the earthquake happened, so the Darjeeling earthquake, which is considered significant. So thereby we combined, so the earthquake hazard analysis plus, so the monitoring of the slope. this is a very classic study, and probably it is a very unique in the world that say the both deterrents, the factors so which have been taken into account, and we created a major slope stability. Say the charts in any given condition. Say the what could be the stability of the slope, etc. Of course, the West Bengal government is so they're taking separately to do the rebuilding of this particular so the slope at a cost of almost so the 150 160 crores. So one single location is costing us so the to rebuild so the 150 crores so the or so. That is the major investigation. The another last, I'm going to close it, so the soon. This is for the metro tunnels. Metro tunnels are shallow tunnels. Overburden is very less, like unlike in the Himalayan region. And then this is the first phase one of Delhi Metro. You will maybe able to Chowdi Bazaar, New Delhi. Then so you have the Kashmiri Gate. This is the particular segment, so which I'm talking, and it indicates that, so the tunnel boring machines are used, so from there to there, and then EPBM, that is the air pressure balancing machines are used, in this section, and then cut and cover. Cut and cover normally we use it, say for the stations, and wherever the stations are there, say the for that, so they you use the cut and cover. So cut and cover technology used, and EPBM, that is the air pressure balancing system. This is a TBM, but it is done in the soils, because the soils do have so the cannot air pressure is there, and when you start actually doing the excavation, so the soil is going to cave in, so thereby to retain that so the air pressure balancing system you need to adapt. But whereas if it is a rock, even if the weathered rock is there in this particular portion, so you have a tunnel boring machines are there. So Delhi Metro now, this is the phase one, but so if you see the phase 4, which is running now, so it is completely spread all the locations. The initial thing is this: the north-south corridor, and then east-west corridors. So they were planned, and the study is so for that particular phase. I'm talking about it. So this is the cut and cover. So you excavate it temporarily, you divert the traffic, and then you put the so the proper say steel foundations, and then so the you put the, of course so the diaphragm walls, and then you excavate it and put the concrete so the so this is the Chandni Chowk. So such a dilapidated buildings are there. A lot of activity. You cannot actually stop that. But so the just 15 meters below, these two tunnels, up and down tunnels, so they are being done through the TBM. So this is that if you have some knowledge, so they about the Delhi, that is the Amar Cinema, so the old Delhi side is going to the main Delhi, and then there is the New Delhi in between, say that. So the TBM excavations were used. The material, what I said is, so the chemical and physical disintegration. Otherwise, rock is, so very good rock, but because of the joints, so the all are, so the pieces, and in some locations, so it is totally disintegrated. And this is the shotcrete. Normally, the shotcrete, 100 mm, 200 mm, so the thick, so the layer will be put. We did the extensive study on the material. So the material is having the different degree, and then assigning the parameters for that, and then um, to do the tunneling. So there is a since I have not actually covered so that aspect so the lecture. What normally we do is so when you do the tunneling, the face, the area you are cutting, say that is going to converge, means so some amounts of volume reduction is going to take place. So before putting the support system, how much volume reduction is going to be subjected to by the cut tunnel? That's a important fact. So the rest of the operations are actually related to that. So thereby, that that convergence of so the tunnel or the phase is what we call is a phase loss. So using so the methods, analytical methods, you will be able to predict so what is the amount of convergence it is going to take place, what percentage of convergence is going to take place, whether it's 1%, 2%, 3%. If your judgment and prediction is good, so then you will be exactly so they're doing that prediction, so thereby the tunnel behaves well. So also associated thing, if you are doing the tunneling there, so it's always a problem of settlements. So how much settlement is going to take place? Because of the settlement, so convergence is also going to take place. So this is what we did it, say in different rock conditions, and then our settlement predictions are, so they're perfectly in line. So which has actually helped the good tunneling practice. So I come to the conclusion that is the what basically I projected is strength and deformation behavior of intake rock, anisotropic rocks, weathered rocks, and jointed rocks through the modeling under different stress state is modeled through physical, numerical, and analytical approaches. So all variety of material conditions, loading conditions that have been so experimented and gained the knowledge. As the physical modeling requires the sensitive and robust experimental facilities, we created these facilities. They are not actually the off shelf, they are available and you have the money and you purchase it. No, with a very minimal, so the money, we could, so create these facilities. So design and development is actually done by us so through HICO, and is that company is actually the major supporter for us. What is that we did? Large scale uniaxial, biaxial, polyaxial testing equipment, servo controlled static and cyclic direct shear equipment, impact testing facility, creep testing, servo controlled high pressure triaxial testing systems, profilometer for the 3D mapping, rainfall impact gauges, high temperature chambers, rock salt leaching setup, which I have not discussed in also the here. To mention a few, which allowed us to pursue a large range of research areas over the years. And this research, this experience, we used it, say for the sustained approach yielded significant new contributions, methods, and criteria to understand the rock and rock mass in totality. And this clarity enabled us to providing the effective solutions to the numerous the ground engineering problems and serving the industry. So this is the sequence which we followed. Basically, we developed capability of understanding the material in different loading conditions, and for that, so we developed certain equipment, and through which so the understanding improved, and using that understanding, so we try to solve that. And I acknowledge, so my teachers, mentors, seniors, colleagues, etc., funding agencies, and unfortunately we lost the Jitendra Singh, the head of the HICO, due to the COVID 2 months back. And but he is the main backbone for us for creating so the good equipment. And of course, so these are the large number of student community all working in rock mechanics, and that this is so the community which is so the doing excellent work so in the earthquake engineering. So this the content of this particular presentation, you can have it very nicely. You can download it. Characterization, modeling, engineering of rocks and rock mass. It is published also in Geotechnical Journal, Indian Geotechnical Journal, volume number 50. This is so the last year, 2020. Okay, so it is a huge article, 90 pages, so the journal article. So you can refer, because this was, so the during the 41st IGS annual lecture, which I delivered at Surat, so the same article has been actually published by the journal. Thank you very much on behalf of IIT Delhi and Professor Alam and all the faculty colleagues and all my participants. So I hope that so you got some information. I have rushed up things, so very fast. But I'm always, so they available, and the information is available for you, so to read. And if you have any queries and questions, I'm there.
Thank you, sir. Very, very detailed and very exhaustive work you have done, and very intensively involved. Very happy to see that what our peers are doing, and you have developed a lot of indigenous technology also. So highly elated to have you, sir, amongst us today, and very thankful for you for your this continuous 2.5 hour lecture also. And I can understand the strength you have with you, and working in rocks need lot of strength.
So,
There was one question. There was one question, sir, that
yeah.
what is the maybe slightly off. What is the schedule for maintaining the TBMs? How often we check our TBMs?
No, for generally, TBM won't take any break. So in a week, so the maybe few hours will be for the maintenance, but otherwise, so the TBM should be in the running condition all the time.
Okay,
Because if it is not actually the running, the boulders will actually the loosen, and that will actually jam the TBM. So thereby, these heavy missions, so they will be always in the running condition, apart from the simple maintenance.
sir. There was one more query from my side that
Yeah,
you have said about the face loss.
yeah,
I was asking this question a day before also, that when we
yeah,
when we are doing either EPBM or TBM,
yeah.
how close we are to the outer walls? Do we
We are also we are, yeah, we are very close. We are very close. That depends upon, so the what is the lining you are going to have it. Like say in metro tunnels, you have, segmental lining is there.
Yes,
Segmental lining is also having a heavy thickness, because it is not that, so the behind the rock is very poor. The rock is able to take the sustain with a nominal, shotcrete, it will work. But for to have a nice view of the tunnel,
yes.
so we are putting the additional segments. But the segments structural strength is also important when you are lifting it, or so, so if it is a very thin section, it will break.
Okay,
So therefore, very thick lining is there. So you need to factor it, so what is your final lining, and what is the amount of phase loss you are going to experience, in the given rock condition. And based on all these things, so you need to, if there is a gap remained, that gap you need to fill it up, so with the additional grouting. So
routing.
you have to do the grouting, you have to do it. Yeah.
So is this phase loss is similar to what we call squeezing?
No, it is different, sir. Like, so the squeezing happens because there is a particular type of stress system is there at a location in a hill, and you are making a hole. When you are making the hole, along that hole, so the stress is reduced, right?
Yeah.
So thereby the rock originally strong, but so now it is a changed conditions, because of this changed, say stress conditions, so it is vulnerable. It will fail. So the cut periphery is going to, so the get squeezed into the tunnel.
Okay, sir. So there was one more question. What is the criteria of volume loss consideration in stratified excavations?
Pardon?
What is the criteria of measuring volume loss in
Yeah.
stratified rocks?
Yeah, of course, it is a very important, so the question. That is what actually underground structures, whenever we do the ground response analysis. Means at a particular location and conditions, how the ground is actually going to respond. Means the moment you cut it, so how much deformation it is going to be subjected to.
Okay.
So this deformation versus the load, so, there will be one can actually plot the relation the load versus the on the periphery, cut periphery, there is a load which is going to come versus how much deformation is going to occur. This is you need to predict it. You need to have a very intense numerical models are there to ascertain so the based on the strata properties you will be able to get it so the what is the deformation. Like say if it is a good rock, you won't get any deformation. Say that even if you cut it so the and without supporting it, the rock is actually going to stand on its own. That is the reason why rock mass classifications. You qualitative and quantitatively you express so the rock in terms of numbers. Those numbers you use it for doing the support design, like armor, Q. My other presentation, I wanted to cover this aspect so that support system can be visualized. So the vis-a-vis the rock condition.
Okay, sir. We will, if we find time, we will request you again.
Yeah, definitely.
We are left with 2 days, and if we
Yeah,
find
yeah,
time, we will definitely look forward to
yeah,
you. And
yeah. I'm most welcome, sir. Like so if it is required, I will be there.
just I would like to say that please share some of your power PPTs, today's
Yeah,
PPT. If
definitely.
not all,
Yeah,
we
definitely.
have a concise one and for
I,
participants.
I will do that, but so even this article, if you see it, say
Yes,
this,
good. Yes,
the
yes.
full text is there. All maybe diagrams are also there.
Definitely, we'll download it and we'll share with the participants. So thank
Okay,
you,
sir.
sir. Thank you so,
Thank you.
sir, for your
Thank
very
you very much.
precious time which you have shared with us, and you have
Nice.
increased our knowledge base manifold.
Thank you. Thank you.
Okay, dear participants, we are now leaving. We will be joining again at 3 p.m. today for the next session. Thank you, all the participants, for your patience hearing and your continuous presence. I'm very happy to see you in the good number. And we will again join at 3 p.m. with a lecture from Engineer Shahzad from Mumbai Metro Rail Corporation.